Hello, I'm Zilin. My presentation is about the problems encountered when synthesizing atomically same metal chocolate ions and several different methods used to solve the problem. Two-dimensional transition metal chocolate ions, that is 2D TMCS, can produce some interesting physical phenomena, such as quantum spin Hall effect, valid polarization, and two-dimensional superconductivity, indicating the potential applications of functional devices. Figure 1 shows the general growth process for the production of TMCS by the chemical vapor deposition method, which is based on the competition between mass flux of the metal precursors and the growth rate of the demand. The mass flux determines the number of metal precursors involved in the formation of nuclei and domain growth, while the growth rate determines the grain size of the growing field. There are usually four possible routes in this process, as shown in the page. However, among the many available compounds, only a few, such as TMC based on molybdenum and tungsten, can be synthesized, usually through the sulfidation, salinization, and tellurirization of metals and metal compounds. Many TMCs, such as TMCs based on niobium, platinum, and titanium, because their metal or metal oxide precursors have higher melting points and lower vapor pressures, resulting in very low mass fluxes that limit the reaction, are therefore difficult to produce. So in this case, many different methods are used to solve the problem of difficult production. Figure 2 discusses the growth mechanism of salt-assisted chemical vapor deposition. Figure 2a illustrates that salt can lower the melting point of metal precursor, making it possible for the reaction to grow two-dimensional TMCS. As an example, the observed comparison of niobium nuclei in the condition of salt-assisted and salt-free is shown in figure 4, like this, indicating the high mass flux of the metal precursor promoted by salt. In addition to the lower melting point, figure 2b shows that some metal oxides can react with salts to form metal oxychlorides, which evaporate at an appropriate temperature to promote the growth of two TMCS. And according to TG and DSC measurements, the precursor melting points of all binary 2D systems fell within the temperature window of 600 to 850 Celsius, as shown in 2C and 2D, which matches the temperature range of the target material growth. Figure 2b also shows that during the growth process, the coarsening forms a stable nucleus, and then atoms and atomic clusters of the chalcogenide and metal are attached to the edges of the growing to the monolayer film and grow rapidly due to their high mobility and proper temperature. Another reason of the rapid growth is that the chemical activity of oxychloride is very high during the reaction. This helps to produce millimeter-sized single crystal 2D TMCs, such as tungsten, niobium, and molybdenum-based TMCs. Also, the density functional theory calculations show that it is more energy efficient to sulfurize metal oxychloride than metal oxide. With this method, Jia Dongzhou's group has successfully synthesized 47 types of compounds, including 32 binary compounds, 13 alloys, and 2 heterostructure compounds. Another method is the hot injection method. Instead of using metal oxide with high melting point, generally metal chloride, carbonyl, acetylacetone, and carboxylate are employed as effective metal precursors in this method. For example, titanium tetrachloride is liquid at room temperature. And also, this method can help promote high quality of 2D TMCS nanosheets. That is, mono dispersity, fast crystal growth, high product purity, and controllable morphology. As shown in Figure A2D, in the synthesis of titanium disulfide nanosheets, carbon disulfide was quickly injected into a solution of titanium tetrachloride in oleolamine at 300 Celsius, forming a single crystal titanium disulfide nanosheets with lateral dimension of 150 nanometers. And also, the figure E shows good size control by the concentration of reactants. Figure F shows that the anisotropic growth of 2D nanosheets is attributed to the large surface free energy difference between the edge and the base surface. This synthesis method is usually applicable to other TMCS, such as vanadium disulfide, niobium disulfide, and tantalum disulfide. Then it comes to the heterostructure nanosheets. Typically, the synthesis of cuprous sulfide on the basal plane of molybdenum disulfide via an ion exchange reaction. In the synthesis of heterostructure nanosheets, the base surface can be used as an ion exchange reaction site, and the negatively charged molybdenum disulfide is used as a basic framework, for it is easier to obtain compared with some other TMCS. As shown in Figure A, it is treated with copper chloride. The introduced copper metal ions are easily deposited through electrostatic interaction. These copper ions spontaneously react with the sulfur atoms in the highly fragmented molybdenum disulfide during the ultrasonic assisted exfoliation process to form the carbon X sulfur intermediate species. As shown in Figure A. And in Figure B, and in Figure B to E, at an elevated reaction temperature of 250 Celsius, cuprous sulfide epitaxially grows in the 001 direction on molybdenum disulfide because the two samples have the same hexagonal symmetry. The epitaxial growth on molybdenum disulfide nanosheets is a general way to prepare two-dimensional heterostructures, such as cuprous sulfide on molybdenum disulfide, cadmium sulfide on molybdenum disulfide, and ferrous sulfide on molybdenum disulfide. Another mechanism approach to synthesize copper sulfide nanocrystals on electrochemically exfoliated titanium disulfide nanosheets has also been demonstrated, as shown in this page. So, in conclusion, although we encountered some problems, Scientists have demonstrated many approaches to solve the problem, including reducing the melting point by salt in CVD, using hot injection method with liquid titanium tetrachloride instead of metal oxide as precursor, producing heterostructure nanosheets through ion exchange reaction, and so on. And we are looking forward to further research on the development of high-quality TMCS and also more efficient applications of them. And this is a reference, and thank you. That's all.